All right, so it's 12:05. We're right on time. Welcome, everyone. This is the UCCS Speaker Series. It's a pleasure to be here with you today, as always. This is the fifth talk of this winter quarter, which continues with our 2021-22 theme of emerging from the pandemic, promoting health and prosperity for all Californians. Well, the pandemic is obviously still with us, but so are a host of other problems, including the ongoing threat from wildfires. In the long run, perhaps we'll garner the will to arrest climate change because rising temperatures and increased drought are, of course, the driving forces behind wildfires. But in the shorter term, maybe we can deploy information technology in ways that help us mitigate the danger. Here to help us understand the potential of information technology and artificial intelligence for proactive wildfire management is Dr. Elke Altintas. Dr. Altintas is a research scientist at the University of California, San Diego, and Chief Data Science Officer of the San Diego Supercomputer Center. She's also the founding director of the Workflows for Data Science Center of Excellence, which specializes in the development of methods for applying computational data science to practical problems. The adjoining WIFIRE lab is focused on artificial intelligence methods to predict the timing, direction, and scope of incipient wildfires and wildfires yet to be. Dr. Altintas is also a popular online course instructor in the field of big data and has reached more than 1 million learners across the globe. She's the recipient of several international awards for research in computing, and she received her PhD from the University of Amsterdam in the Netherlands. Before bringing her on, just a word about questions. As per usual, you can type your questions into the Q&A feature of Zoom or ask your question live at the end of the talk, but we will be reserving questions until the end. But please type in your questions in an ongoing manner if that's what you wish to do. Just remember to provide both your name and affiliation. All right, well, without further ado, please join me in welcoming Dr. Elke Altintas.
Thank you so much for the generous introduction and having me here today. As you heard, I'll be talking about fire from a use of technology for proactive management of its perspective. And fire, as you know, is, or as we got to know at our time, is a destructive thing because we got to know wildfires when we cannot control them. And in 2020, even 10 billion acres burned with lots of economical damage and property at fire response costs, lives lost. So I don't think I have to, change or recite all these figures that we all got to be very familiar with. But I think we are getting used to these images that are almost apocalyptic during the fire season, which is now almost year-round. And what I think here to say is this is not normal because they are mega fires, but fire is actually a natural thing. It's an inevitable part of nature. And there are some reasons why we are here today and experiencing these mega fires. One of them, of course, is the weather change. Our climate and weather is changing. And that's affecting and driving these fires. A lot of these fires are actually weather-induced. If you look at the same ignition point in LA, in Topanga Canyon, this is just a toy example, so to say, but that ignition point would grow a little bit, but it grows up to 480 acres here, and there's some population and housing, but this is probably a quickly suppressible and manageable fire. When we have the effects of high wind and fire weather, so to say, in Southern California, we call them Santa Anas in the San Diego area. Every region has their own fire weather. And we look at a fire weather day, the same ignition point can turn into a mega fire in a matter of hours, and it can get out of control a lot faster. And hitting that fire hard and quickly can help managing that a lot more effectively and even maybe avoiding it. The other thing, of course, again, climate effects, we are dealing with the worst drought in history. So everything is dry and waiting for a spark at the time to turn into a severe situation when the right conditions hit. And on top of that, we actually have a lot of vegetation accumulation because we've been suppressing any fire we can. And some of these fires nature needs. So I refer to these here as good fires. When the fire is natural, it actually gets used by nature to clean itself or do some processes, right? Even like some vegetation won't see it without the fire. So this natural cycle, when we start suppressing these fires as effectively as we can, turn into, it's a little counterintuitive, but we have too little fire in the landscape that is of good nature, and this turns into an accumulation of vegetation waiting for a spark. This is referred to as the fire deficit, and that accumulation under the right condition leads to these destructive mega fires that we are experiencing today. So there are a number of combinations, and on top of that, we increased our impact in the wildlands at the wildland-urban interface. So there's a lot of human activity creating spark when the right conditions happen again. So there's a number of different conditions, and there I think we can cut to the things that cause this problem and maybe proactively deal with this. The good news is fire behavior can be modeled before, during, after a fire, and there are different ways to use that model. To model a fire in general, you need to have some environmental sense of weather, fuels accumulating, that's the vegetation, and the landscape. But on top of that, there are different ways we can capture the fire's behavior. And when we have operational and physics-based coupled models and many different types of these models, how can we pick one to fit different scenarios? That's going to take some analysis and understanding. And these models that become the simulations for fire behavior, they run under different speed requirements, and they have different complexities and inputs of different complexities they depend on. But when we are dealing with fire response, for instance, we need something to run fast and made available to the fire management officers or decision makers managing the fire. So that you can probably deal with less complex situations because there's real-time data as well, and adjusting and learning about the behavior of the fire using that real-time data becomes possible. So that's the type of approach I'm going to talk about partially today. And when we talk about community planning, and we hear a lot about fuel treatment optimization these days, the complexity of those models start going a little bit on the complex side, but we can take our time with some of them. We can have things run, and computational complexity we can deal with, input complexity we can deal with in a little longer time span. And as we go towards sustainability and other types of decisions, we see that applications using these wildland fire models can be pretty variable. And as we move from that to using these models and relating data to these models, we need to think of it as there are existing models that are useful and is being useful, and that could be updated and adjusted with data to the current conditions. And there are next generation fire prediction models that have really detailed inputs, and their ability to take advantage of data is actually a lot more detailed and complex, but the results of it are a lot more beneficial in the context that we are using them in the applications that become solutions to specific questions. So then we can couple these as next generation fire prediction models and how we combine them with emerging data science and sensing technologies. And these involve better forecast and modeling, ground-based weather stations or imagery. We have a lot of cameras that's coming into the picture today. Remote sensing through satellites or overhead sensing through remote objects like aircraft that can fly really high or drones that fly a little closer to the fire. So we can understand about the current conditions through sensing, but also we can use sensing to understand the landscape a lot better in a lot more detailed way, using things like LiDAR sensing prior to the fires or sensing over and over to ensure we improve and expand our understanding under dynamic conditions. What this becomes available to is what we call data-driven fire preparedness, mitigation, and response. And this requires, as I'm going to talk about today, continuum of computing and data technologies, and also use of data in the best possible way, which requires machine learning, AI, and data science techniques to be available to solutions that will make use of fire sites. But if we get these right, I think in all phases of emergency management, from preparedness to mitigation to response and recovery, which is the phases of the fire during, after, and before wildland fires, we can effectively build solutions as situation is changing, and dynamically adjust our solutions to the changing situations. And what I'm going to talk about is how we are doing this using continuous iteration and integration of AI, and many forms of computing are also being used for these technologies. And I am from the WIFIRE lab. I'm the founding director of it. Our mission in the lab is exactly this. We do research and development toward solutions, so practical wildland fire solutions that span mostly response and mitigation. And we couple or base these solutions on next generation fire science techniques that couple our expertise in data computing and artificial intelligence to the science community. And with what started as an NSF project and a demonstration exercise turned into quite a bit of new technologies and solutions over the last decade, or a little bit more than that. So in our first project that we had, our goal was demonstrating data-driven fire modeling, because in San Diego, we had a denser data availability about the weather and the environment, which turned into initially a collaboration with LA Fire Department, LA City Fire Department, which turned into a tool we refer to as FireMap for initial attack. So this is really the initial phases, first couple of hours within a fire, how we can monitor the ignitions and model the potential effects of that fire or the behavior of that fire, so that management decisions can be taken through that. And over time, this was coupled to an aircraft program that gives real-time information about the perimeter of the fire almost as soon as the fire starts. In the first couple of minutes to half an hour, the models are available and aircraft perimeters are available through this program, which we refer to as the FIRES program, Fire Intelligence, Fire Integrated Real-Time Intelligence System. And right now, this program is funded by CalOES, California Government's Office of Emergency Services, and led by both Orange County Fire Authority, CalOES, and in partnership with CAL FIRE. So we are really excited about the developments there. But over the last 5 years, this particular system was used by thousands of firefighters in 100+ operational fires that got managed through these models and the aircraft perimeters. And what is the AI in here? When you're modeling the real-time fires, characterizing the dynamic fire environment becomes very important. What does that mean? Variation of wind from different sources of information, smoke, moisture, fuels, fire perimeter. So a part of our research is how can we get as diverse as possible in terms of the inputs we are collecting in real time and curating through AI and data management techniques, so that they become available as inputs, the most accurate inputs to these fire behavior models and ensembles, which, by the way, we are updating also with a suite of fire models on top of the existing fire site-based models we developed over time. And the other part of it is, how can we get ignitions right? You know, there are ignitions available from 911 calls and other systems like satellite detections. Through a manual, human-based approach, we actually turn those ignition information from different sources into an ignition point that's triangulated between these sources. So we can make that initial fire perimeter that we are providing as accurate as possible as those inputs. And one of these is definitely detection from cameras that are available in the landscape. And when we do these over time, every 15 minutes or whenever new data is available, remodeling so that we can calibrate the fire models with the real-time information about the dynamics of the fire behavior itself that's being available, has been our approach here. And you know, here, of course, one of the methods I talked about was deep learning-based smoke detection. Right? These techniques require labeled data. When we do that, we also work with labelers and modelers or fire experts to create images that other AI researchers can use. So this type of techniques can be available across different systems that are providing imagery about the fire, and that can be deployed to these different systems a lot more openly, transparently. And our goal here is to improve the field through and enable community-driven collaborations on top of such data sets. And another thing that you'll need for something like this is computing. So for our partners, we also provide computing resources that they can build AI techniques and methods and deployable containers about these different phenomena, so that we can collectively build solutions and as a community develop solutions over time. And I left one link here for a publication related to this smoke-based detection techniques that we developed. But that goes to say there are many others developing these smoke detection techniques. And I think real deployment of these techniques over time will be available in operational real-time systems. I think we have a little bit more times to go as the AI community. And here is, I think, also a thing to mention, that we need to be careful about deploying AI into the solutions. And our approach has been, we develop the techniques and we introduce them to these systems when we are sure they are ready. So that link between practical needs and the technical developments, evaluation of that is a big part of applying AI in the context of this real-time response and operations. But our team also recognizes, even with the best of the techniques and possibilities, when you're reacting to fires, we are really in the fighting mode. So a part of our approach has shifted towards expanding our technological toolkit to proactive fire mitigation, especially starting with conducting prescribed burns as one of these proactive fire mitigation techniques. So what does prescribed burn mean? It's actually, in a controlled way, putting low intensity fire on the ground to clean up some of the vegetation and maybe mimic some of the natural processes that the nature needs, so that when a true wildfire scenario hits, the fuel structure that's available is less destructive, and the wildfire actually can be a lot less destructive through that. So the goal here is to reduce the accumulation of fuels through vegetation management. I think this has been on the media a lot, and I hope it's something that you're all familiar with. But recently, in 2022, the infrastructure law that was signed, one of the things is actually prescribed burns and confronting the wildfire crisis, so to say, through ramping up prescribed burns by some multipliers. 4x is the measure that's put in there. In California, we have the million acre strategy, which becomes actually 10x from the current practice. So there's a lot more need, and the need for optimization here also comes with it. So one of the things we are doing through National Science Foundation Convergence Accelerator support is creating a tool that we refer to as Burn Pro 3D that can help link next generation fire science and AI to optimize prescribed burns, so we can attempt to providing maybe techniques and windows for burns that enable the management communities to burn at the scale that these new goals need. And we have a number of partners here that we are working with, but the persona, so to say, who our users would be for Burn Pro 3D. For instance, land managers can use these tools for identifying high-risk areas and prioritizing at the regional scale where to burn and how and when and where to burn, so to say. Burn planners can optimize through science-based tools, prescribe fire windows and prescriptions for basically controlled burns. And that's also comes with understanding the conditions and when those conditions can happen. So this is this careful optimization on when and where to burn. And then burn implementation on the day of, taking go, no-go decisions safely, and reevaluating the risk is a part of our goal here as well. And this is all powered by a platform that we built and that powers all of our solutions, the WIFIRE Data and Model Commons, or WIFIRE Commons in short. And I'll talk a little bit towards the end of my talk about WIFIRE Commons and how you can engage with it. But when we think about it, what we were trying to do for response is different than what we are trying to do in prescribed burns. And that initial thought I shared about, different applications require different types of models, or effectively using multiple models comes to play here. In this context, when we are talking about removing vegetation, we first need to understand the 3D structure of the vegetation. So we need a fast 3D way of understanding vegetation and coupling that to models that can take advantage of that 3D vegetation at the scales prescribed burn needs. Here, just to give you an example of that, in FireMap, what we used was initially the Farsight model from US Forest Service. Then we adjusted that with real-time weather. You just need their two-dimensional weather and 30-meter resolution of two-dimensional fields. And what we get from that is this two-dimensional fire perimeter overlaid on a map, which tells us about rate of spread, where the fire will be in the next half, 1 or up to 3 hours in this case. And that is different when it comes to prescribed burns. We need models that are 3D, so we can understand truly the fire behavior. So now we are working with a new tool, a fire modeling software called WIFIRE, that gives us a quick way of solving the 3D fire behavior, and also tells us about behavior of the fire from the fuel consumption perspective. When the fire is put on the ground in a prescribed burn, the goal is not to torch through the whole environment and remove everything, but to clean carefully in a way that reduces the wildfire risk and keeps some of the natural vegetation there. So what's the fire consuming from the environment, and how that consumption turns into emissions, and how those emissions transport in the air and what communities it hits. That's the type of behavior we are talking about when it comes to prescribed burns. And for them to happen, you need more detailed inputs, like a 3D weather at 1 meter resolution compared to the 30 meter we had, is something that we are working on. And ignition patterns, how can we optimize how and where to put the ignitions when they burn the landscape using the prescribed burn practice. And we also talk about 3D weather and different ways of having the weather and extrapolating it in a way that we can have it as the detail these systems require. And our goal, since we have a quick access to these models, in Burn Pro 3D, we start with getting a burn unit and running as many ensembles as we can about that burn unit. Again, we can take our time here because we are running scenarios, and they become the basis for the rest of the optimization that takes place. So in this case, what we are looking at up here is on the center is Piedmont area and some ensemble that was generated for it. And what you're looking at on the right, at the bottom right, is the burn unit in Yosemite stud horse, and under different ignitions, like strip ignition, ring ignition, counter ignition, under different conditions. There's about 900 runs there. And this is one ensemble, and the goal is to generate thousands of those so that we can make informed decisions, science-based decisions, and couple those to things that can help us make these decisions. Before we went into this, of course, we worked with the communities and AI, fire science, and practical management communities. And two things were apparent. We need next generation fire modeling, but for that to happen, we need high resolution 3D dynamic fire environment data, fields, weather, and other things. And we need to improve speed of running these models, flexibility of running them, and interpretability of the model products. So that's what we focused on in Burn Pro 3D. One of the things that we've done was conditioning of the inputs, working with US Forest Service, Tall Timbers Research Lab, and Los Alamos National Lab. We worked on continental scale, 1 meter resolution model of the fields. As I mentioned before, this compares not just to 2D to 3D, it's a 900 times detail, even in 2D, and it has this vertical component that you can have characteristics of the field, and we can on-ramp sense data through LiDAR and other means into these fields to keep those current and accurate. And when you talk about sensing, you can have different ways of doing it, different ways of characterizing it. So the techniques we are developing now are how do we automatically ingest if there's a terrestrial or aerial LiDAR about an area like we had in Yosemite, so we can have the best fields for the ensembles before we actually execute them. And these are being used in different ways. So this is actually Blodgett Forest in California, and there are fire cameras there, alert wildfire cameras. And when you look at those cameras, you could see the tree structure, and you could see a little bit, there are some dryness there, or if you zoomed into it, there could be some more obvious. But in that area, when you turn those into 1 meter resolution fields that the models can take advantage of, it looks like the one on the right. 1 meter, and we talk about the 3 species, what's on the ground, its surface area, volume, density, moisture, so that we can have a representation of what we are looking at in an environment in a way that feeds an executable fire simulation. And the result of that fire simulation will be in Yosemite National Park, those ensembles I showed you here. Now, this is the initial on the left fields that we start with, let's say in stud horse here, stud horse, it's a burn unit there. And on the right, what we are looking at is the visualization of what the fire would consume and what it would leave behind under a certain set of conditions. There are many versions of these. And there are ways to visualize surface and canopy consumptions or other objectives related to the land, so that we can quantify a lot more effectively, and maybe we can take some risks or less risk, or we can maybe expand objective windows to enable burns on more set of days. So the goal here is, can we expand burn windows for these areas that enables burnability or burning on different days. So what other AI techniques are being used here? These are models that are being generated, and they are used to improve fire behavior models and their speed, and creating emulators that can actually capture fire behavior about these different environments on an ongoing basis. So when conditions change, let's say the day off, we can quickly decide if the risk changed or not. Optimization techniques to address trade-offs. These could be from the risk of the fire to weather patterns, ignition pattern optimization, or smoke optimization. So these models actually can give us not just the consumptions, as I mentioned before, but emissions. And as the models are improving and we get more understanding of what emission means in the context of these hard fuels, that becomes coupled to smoke transport models, and that you can think not just for air quality, but also public health type of scenarios can be turned into solutions here. And while we are doing this, we are using visualization and explainable AI techniques so that we can increase understanding of what the user is looking at and how the decisions can be made based on those all along the decision-making chain, and the scientists themselves using these as well. And also, increasingly, we are working on public acceptance and understanding using these models. So what I showed until now was coupling quick fire and also fast fuels to quick fire models, and using those models in the context of decision support tools, in this case, the Burn Pro 3D. So this is, I think, the way we'll see more and more how AI and science integrate into solutions. It doesn't just have to be fire science. We are seeing it in all kinds of domains. But when it comes to fire, I think we need collaborative environments that build on open, community-based, science-driven models that can be transparent to the solutions. And I think the future is very collaborative in this space. Community is becoming very collaborative, and we'll see more and more solutions that come out of such partnerships, consortia, and collaborations. So to enable such collaborations, we started thinking, how can we expand our cyber infrastructure and technological capabilities to enable others? So, and data sharing and AI is the bridge here, is one of the bridges at least. And we provide the knowledge management and other types of capabilities ourselves, of course, but how could we enable others to work with us or find the data they need, find the models they need, and in a way that they can execute them as services, so they also can build their own solutions around it. So Data Commons is the platform that we share and enable data from a number of different parties, and we federate these data, and they become services, programmable services that can enable other applications. One thing to mention here, for instance, San Diego Gas and Electric. We work with San Diego Gas and Electric, and they generate quite a bit of data on a daily basis about the weather, about the environment, about the fire potential. Now that data becomes available with the science communities and others in viewable forms too, in visualizable forms. And that enabled a number of others to use the SDG&E data, which wasn't possible before unless a disk or some storage device was mailed around. And the other part of it is, once we have this, we add AI techniques together. For instance, we were able to build some vegetation management practices using AI insights, using the insights generated from AI together with SDG&E, which I think become very productive. And the other part of data is models. Models can be physics-based models, these fire simulation models, but they can be AI models, which curate the data, which make the data a lot more accessible by others or understandable. So there are many ways, as I mentioned before, you can use AI. But if I'm an AI expert, how do I find the data? How do I find the right libraries and computing environments? So our AI gateway is that environment that community can come and build AI models, and they could be deployed as containerized units in the model commons that we are building. And in our case, of course, as I mentioned, we are using quick fire, fast fuels, and also Farsight from US Forest Service, to build our own solutions in a use-inspired way. And we started here by FireMap and Burn Pro 3D. And WIFIRE Edge is another new platform that we are adding so that edge AI and computing capability can find solutions in the fire space through the type of framework connectors that we are building into WIFIRE Edge through support from federal agencies. So I'm not going to talk a lot about this slide, but when we talk about commons, what's the infrastructure? There's the model commons and there's the data commons. They build on knowledge management infrastructure and techniques like OWL or Pangeo and different file formats that are generally used by the community. But there's a whole flow of events. If I'm a person who is trying to do a scenario generation through fire modeling, which fire model am I going to use for my application? And can I find that fire model, play with it, find the right data sets that fit that data? And there's this connection between the data and model commons in terms of not just the structure of the data, which is the resolution and both spatial and temporal resolution of the data, or the formats of the data, but also the context, concepts that relate to fire. What does that data mean? And how can we relate these models and data sets to each other and map them without having the human do a lot of the work? So that's a part of the work here. And we built the first fire modeling ontology to back this platform in a way that's compatible with environmental ontologies like ENVO. And knowledge graphs like Nowhere Graph that's compatible also with Google Data Search and other big tech capabilities. So the goal here, again, is to create an environment that we can create interconnected bits of things that are executable and that can collaborate and be mapped to each other, or we can be related to each other through data. And while we are doing that, we keep track of the provenance of who is doing what and what the model products are, which version of the model was used, and all those different things that we refer to as the provenance of that whole activity. So we can explain how that output that we are seeing or the result that we are seeing came to be. What we are also doing is when the model products become available and they go into solutions, they become like, if they go into an AI-based solution, the input to that AI and explainability of that is very important. So all the fire ensemble runs, for instance, are kept as objects, digital objects with identifier. This is the digital object identifier. So they can be referred to at all times with that identifier, and we know that data set won't change. So this improves the responsibility aspect of the work and transparency of how these tools work and their limitations, but their also explainability. And here we are making use of the EasyID from University of California for object identifiers, but there are different object identifier methods as well. Another thing we are doing at the end of my session, I'll have a few more minutes here. We are also focusing on education, but not just education in an academic sense, at the intersection of science, technology, and society. So we are building platforms and techniques to increase situational awareness by the public. Even FireMap itself, I think, had a big role here. Every fire, this is an environment that, without seeing the models, like the simulations, anything that's publicly available to the public about the fire itself becomes available as layers within FireMap. So we have millions of people coming to our sites for situational awareness. Again, we don't make predictive models available to the public here, but we have everything else available as layers, and predictive ones are only available to decision makers. One of the things recently we've done, and we are pretty proud of, and I would love for you, as I'm talking, look at the names on these posters. We created a challenge with UC San Diego students to increase public understanding and acceptance of prescribed fire. What can be done? And the students worked over a course of 36 hours was introduced a week before. They came back, we taught them some design techniques and created all these wonderful ideas about how we can install some public installations. We can create public installations in visitor centers, museums. You know, we are working with STGNU on some, so that we can explain the public. Wildfire is scary maybe, but wildland fire doesn't have to be scary. And when there are prescribed burns, the public could be a part of the solution, and they can accept that a lot more effectively without increasing, without fear, or with limited fear, I should say. And the students also presented their work at the panel design lab, and we collaborated as a part of California 100. That's California's feature over the next 100 years. That's the redesign approach for it. And we selected 7 of these teams. We liked them so much, we couldn't pick one winner. Over 80 students and 23 teams we started with. And 7 projects were selected to build their prototypes over the summer for this purpose. The other thing we are doing is we are working with high schools and engagement programs through Global SchoolNet is our partner here, to create understanding of fire weather, what kind of careers are available in this, and some other programs, so that we can start engaging with the public early on to understand the problems and solutions for those. And another thing is, I think in our region, especially in San Diego, we need to think across borders. Fire is across the borders. We have borders both to Canada and Mexico. We've been participating in this wonderful program called Enlace. It's a 7-month residential program. And one of the teams, for instance, last summer in Enlace worked on replicating FireMap in the cross-border context, especially applications to Baja California in this case, in a bilingual way. So this way, I think we can increase our ability across the border to create solutions at the international scale and manage climate-driven challenges together. And as I mentioned, we are very collaborative, and we work with real problems and users. We take our research challenges from the practical community. So our approach isn't science and technology to practice, but it's bi-directional. We learn from the practical communities and translate those into challenges for ourselves. And we also, of course, try to offer or explain what can be done to practical communities, so that we can maybe inspire different solutions driven by practical communities. And our biggest goal here is to enable new science and solutions through AI and data and use of computing. And it's built for extension, the platforms we have to different hazards. We are already working with mudslide and flood communities to see cascading hazard effects, fire and earthquake, and response and recovery. And we also worked with, even over the pandemic, to use some of these tools for COVID-19 personal level predictive solutions. So I think hazards we need to think of as related to each other. And I think once we start learning to collaborate through data and using data as that collaborative currency, we'll start seeing these solutions a lot faster, and we can create the right culture around solutions, which we need really badly these days. Thank you. And I left some links to WIFIRE at the end of my presentation before I take questions from the audience.
Yeah, I'm going to just jump in. Thanks for such a great talk. There's a lot of questions lined up on our Q&A about, I guess, good fires, prescribed fires, but I have a question about bad fires. So like in assessing the prospects for identifying and extinguishing small fires before they get big, what is the rate limiting step? Is it like we don't have enough data being collected from sensors? Is it that we don't have the processing power to deal with the data or the models to do it? Or is it once the data are assembled, do we not have the on the ground response forces, emergency response forces to take care of the problem before small problems get big?
I think all of that is at play here. It's a very complex question. I think overall ignitions and ability to detect those ignitions as fast as they happen is one of the methods here that I see practical communities using. So through these tools, actually, a number of the fires get detected, and they are done before we hear about it, and it could have been bad fires. So I think there's going to be a balancing factor here, right? Which ones to deploy for, and any fire we deploy, or California at least deploys for. And in the fusion center, for instance, we detect every, we look at every ignition, and every ignition gets modeled. And we confirm that ignition from not just cameras and satellites and other forms of information, but also ground collaborations with the radio communication and things like that, and 911 calls. So when a fire ignition is reported, I think the ability to hit them fast is pretty good right now. And even then, with the best of the intentions, sometimes, of course, things can be delayed or things can get out of control. And I think that's what we are experiencing when we hear about these fires today. But it could have been a lot worse. I think there's a lot of work in this early detection, right? The camera systems are also being used. There's a lot of progress in that area.
Thank you. I'll turn it over to Cindy to guide the rest of the questions.
Thank you so much, Dr. Altentis, for just a fantastic talk today. And with that, I'm going to go ahead and let Brooke go ahead and stop our recording.